All right, so I want to introduce the topic of interference of a light in this video. I am going to talk a little bit about the theory behind it. It does require us to see some demos. I'm going to show you the demos the next time we meet. It is much easier to see these demos in person than me talk about them in a video, to just show them in a video. So when we meet again, I will have some demos on interference, and it'll help you to understand these concepts. So we're going to be talking about interference with electromagnetic waves. Now, the conditions for interference of electromagnetic waves really the same as the conditions for interference, or pretty much the same as the conditions for interference for mechanical waves, except for the fact that we're dealing with transverse wave as opposed to longitudinal waves, and it does put some restrictions on some of the conditions. So we know, for example, for mechanical waves, if the path difference between the two waves at the observer is some multiple of n lambda, you're going to get constructive interference. That's going to be true also for transverse waves. However, there's other conditions that we need to consider in order for us to observe them. So I'm going to talk about that a little bit. Okay. We are in the realm of optics where we actually have to treat light as a wave, and we call this physical optics. And so in chapter 37 we focus on interference, and in chapter 38 we'll focus on diffraction. So we'll start with interference first. And interference is really the effect when two or more waves of the same kind exist in the same place at the same time. They basically add together. The question is, what conditions must be met in order for me to observe interference with light? And I'm really going to focus on visible light, although this is also true for other types of electromagnetic radiation. I want to focus on visible light because we can see the effects very easily. Now, just like in the case of mechanical waves, sound waves, for example, the sources have to be coherent in order for us to observe interference. The phase relationship between the two waves, or the phase difference between the two waves at any point in space, has to be independent of time. If they're not, if the phase relationship changes with time, you won't be able to observe the interference effect. And that's true with sound waves. And of course, it is much easier to observe interference with a single wavelength. And of course, that was also true with sound waves. And again, in parallel with sound waves, the superposition principle must apply. If you really want to be able to observe the interference effect, do you want to see, in the case with light, you're going to see light in bright spots on a screen. You have two waves interfering with each other, and you look at you project the effect on the screen, you're going to see light and bright spots. They're called fringes, dark and bright fringes. And it's easiest to see if the intensities of each of the waves are nearly equal, because that means you can get complete cancellation. If you don't have the intensities be equal, then it's hard to see where you get complete cancellation of the waves. You won't get it. And so it's going to be harder to see the effect. You're just going to see a difference in intensity patterns, which depending on the difference in intensities of the waves might be hard to see. And this is also true for sound waves. And if you have we talked about the interference of sound waves. If the intensity of the two waves are different, it would be hard to hear the interference pattern. It would actually, if you had two speakers in a room playing sound, and the intensities were different, and you walked around the classroom, it would be actually hard to find the locations where the minima occurs. Now the last one, this is really due to the characteristic of transverse waves. Transverse waves can be polarized. We're going to talk about that later. And because transverse waves can be polarized, there are certain conditions that must be met in order for us to be able to observe interference. The state of polarization of the waves cannot be perpendicular to each other. Remember when we talked about electromagnetic wave, every time we drew a picture, the wave was oscillating in a plane. That oscillation in a plane is called polarized light. If you have two waves oscillating in planes perpendicular to each other, and they interfere with each other, you're not going to be able to see the interference pattern. And in fact, this is called the Fresnel-Arago law. And there's actually some categories regarding this law. For example, if you have two linearly polarized waves in the same plane from the same source, they're coherent, they can interfere. Two waves linearly polarized in perpendicular directions cannot interfere. Two linearly polarized waves that are orthogonal, they're perpendicular to each other, originating from the same source, can actually interfere with each other if one of the waves is brought into the same plane of polarization as the other wave. And the key thing is from the same source, because then you have really coherent waves. If the two sources were not coherent, then you could not rotate the plane of polarization into the plane of the other wave and observe interference. That would not be able to be observed because you have two incoherent waves. If the inherent phase difference between the two sources is time independent, then we say that the sources are coherent. The time in which the light source oscillates in a predictable way is called the coherence time. All real light sources are temporarily coherent. And generally speaking, light sources produce waves in bursts or packets or wave trains. Each packet will have a different phase. There are cases where the phases from each source are nearly the same. For example, the laser or light passing from a single source through two slits. Then that would be an example of coherent sources of light. So in order for us to really be able to observe interference, the sources do have to be coherent. So again, like I said, we can observe this with lasers, but we can also have a light source send light from a single light source through two slits and allow them to interfere with each other. Now, what are the conditions for destructive interference and constructive interference? Well, they're the same as really what we described before. The phase shift has to be some odd, or the phase difference has to be some odd multiple of pi, where n is an integer. And really this means that the path difference that each wave takes, the difference in path taken from the wave to the observer, is an odd multiple of lambda over 2. It really means a peak and a trough of the wave arrive at the same time at a particular location in space. For constructive interference, the phase shift between the two waves, or the phase difference between the two waves, has to be some multiple of 2 pi. That means the peaks of the waves arrive at the same time at a location in space, or the troughs of the wave arrive at the same time at some location in space. In other words, the path difference is some multiple of lambda. In 1801, an experiment was carried out by Young, and I will demonstrate this in the lab. Although I will use lasers, he used candles, which provided strong testimony for the wave theory of light. However, really to make the theory more convincing, it required the work of Fresnel to convince all scientists that light is a wave, that the wave theory is a valid way of describing electromagnetic waves. So here's an example of his experiment. You have a source that's not, you have a source, and the light waves go through a slit, and then these waves then go through these two slits, and these waves interfere with each other, and when you look on the screen you will see a bunch of bright spots and dark spots. This is called a fringe pattern. The light spots are called bright fringes, the dark spots are called dark fringes. The dark spots represent locations where you have destructive interference. The light spots represent locations where you have constructive interference. Again, when we get back in class, I'm going to show you a real life demo of this. So I want to talk about Young's double slit experiment, the condition for producing constructive and destructive interference. Normally this calculation is actually algebraically tedious, but as in the case of Young's experiment, we can make some simplifying approximations that will make life easy for ourselves. So what I want to do is derive the equation for Young's double slit experiment. So let me go to the board, draw a picture of the system. Let's see, let's draw an axis. And then we'll draw a screen on which we will observe the interference pattern. And let's make this a dotted line. This is an axis. And you'll have two slits. We'll have this slit, we'll call this 2, and this bottom slit we'll call this 1. And we have some source of light. The light goes through the slits. And let's say we have a location here where we have a very bright spot. Let's call this distance y. And let me look at the distance traveled by the wave going through slit 1 and the wave going through slit 2. Okay, now ordinarily what we would do to analyze this problem would say, okay, I have constructive interference there. Let me call this path R2. Let me call this path R1. And what I would say then, R2 minus R1 is going to be some multiple of lambda. And when we do double slit interference, the integer is denoted by the letter m. Now, R1 and R2 can be determined by the Pythagorean theorem, right? This distance squared plus this distance squared, right, will give me R1, and then the distance from here to here squared plus this distance squared will give me R2 squared. And we can solve the problem. You just have a lot of square roots in it. It's not an easy problem to do. In fact, I'm going to do an example. It shows you how complicated the algebra can be. However, in this example, lambda is small, L is large, and this separation is small. And so we can make a simplifying approximation to make the math easier. Now, because L is large compared to this separation, and let's call the separation between the two slits D. So let me use another marker. We'll call the distance between the slits D. Okay, so this distance is D. In my description, I'm going to assume that the slits are very small. They're basically point slits. Okay, they're very small slits, and the reason why I'm saying that because if I make the slits finite in length, I have to worry about something called diffraction, which we'll cover in the next chapter. So I'm going to ignore the effect of diffraction. Basically, the ratio of this distance to this distance is almost 1 because of the fact that this is huge compared to this separation. This angle and this angle are approximately the same. And one can go through the algebra to show that, to actually show that R2 minus R1 is a small number and basically equal to the following. Because these angles are about the same, I'm going to do this. I'm going to draw a line perpendicular here. Again, like I said, this angle and this angle are about the same. By construction, this angle is theta. This is a 90-degree angle. That's a 90-degree angle. You can easily show that this angle theta and that angle theta are the same. And really, then the difference between this and this is just this guy. And so our path difference is just this thing, which is d sine theta. If you derive an expression for R1 and derive an expression for R2, and then you do an expansion for the case where this is large compared to that, you can show that the path difference is approximately equal to this. I'm not going to go do that. I'm going to assume, I'm going to have you believe me that that path difference is approximately equal to this. And so then I can say that d sine of theta is m lambda. Where m is an integer. M can be 0, 1, 2, 3, etc. What does m equals 0 represent? Well, it means that the two paths, the path difference is 0. We're talking about right here. You're going to get a bright spot right here. So get a bright spot here, then you'll get a dark spot, then a bright spot, then a dark spot, etc. And this is called the order of the interference pattern. Okay? So basically we make this approximation that this is the path difference because we're saying these angles are about the same. So that's the condition for constructive interference for the double slit experiment. That makes the math way easier as opposed to calculating this from geometry and this from geometry. I'll show you. I'm going to do an example. You'll see what I mean by the simplification produced by this problem. Now, if we have destructive interference, of course, if you have destructive interference at some location, let's say here, you have a dark spot, then the path difference is some odd multiple of lambda. And so for destructive interference, you get d sine theta equals m plus a half lambda, where m again is 0, 1, 2, 3, etc. I do have the equation for intensity shown there in the slide. I will get to that equation. So these are the results. This explains the Young double slit experiment, the condition for constructive interference and destructive interference. Now, we can say one more thing. We can say something about the location of the max or min. We can solve this for y. Isn't it true from geometry that y is L tangent of theta? If theta is much, much less than 1, and you've got to be careful with this because this approximation does not always work with interference. Okay? If theta is much, much less than 1, then y is equal to L tangent of theta, which is approximately equal to L sine of theta, which is approximately equal to L. Now, if this is a bright spot, then you're going to get m lambda over d. Where did I get m lambda over d? Well, this is the condition for constructive interference. If I solve for sine of theta is m lambda over d. So I put this here. So this is for a bright spot. Again, this has to be true. For a dark spot, that's going to be equal to L m plus 1/2 lambda over d when theta is much, much less than 1 degree. I'm just 1, sorry. Actually, yeah, 1 degree. Okay. I'm using that in degrees, but if you want to do it in radians, you can just say when tangent of theta is approximately equal to theta. Okay. When tangent of theta is approximately equal to theta, then we can say this. But this typically happens when you're less than 1 degree. Actually, I should say less than 1 degree, not much, much less than 1 degree. Sorry about that. So when theta is less than 1 degree, tangent of theta is about equal to sine of theta. When you get above 1 degree, that becomes a problem. Okay? You can always use this equation. Y equals L tangent of theta. You only want to use this or this when the angle is small and you know whether or not that's a bright spot or dark spot. This works no matter what. Let's take a look at an example where we have to do a we can't do the approximation. I did a similar one to this with mechanical waves. Okay, the values there are such that D and L are close to each other. D is 1/3 of L. In this case, D is much, much less than L. So how do you tackle that problem? Well, you can't make this approximation in this case. So I have a source here. I have a source here. And I have a vehicle over there. Actually, let me draw that better. So let me draw my R1 and R2. Okay. This distance is 300 meters. And this distance is 1,000 meters. And we want to calculate the wavelength. It says if the car is at the second maximum, so when this is 400, if the car is at the second maximum, what is the wavelength? I cannot use this equation because this distance is comparable to that distance. I actually have to do this by brute force. I actually have to figure this out. Well, this distance is going to be, if I draw a right triangle, it's going to be that. So it's going to be 1,000. This is going to be 100. So this is going to be the square root of this distance actually, let me check my math. I think I made a silly error. That's 250, not 100, sorry. This distance is 150. So 400 minus 150 is 250, sorry. This distance is going to be 150 plus 400. So this distance is 550. So you're at the second maximum. What's m at the second maximum? Well, the first maximum is right when you're right in between, because the path difference is 0. M is 0 in that case. The second maximum occurs when you're one wavelength apart. And so the path difference has to be equal to one wavelength. The path difference is this minus that. And when you do the math, you get 110 meters. Oops, let me double check. Yeah, one. That's the wavelength. Now, the next question is, how much further must this person travel to encounter the next minimum? You get a maximum here at lambda. The next minimum is going to be a 3 lambda over 2. And so I got to drive a certain distance x so that I get a second minimum, or the next minimum. If this is x, this distance is going to be what? Or this distance is going to be x minus 150. And this distance has to be x plus 150. And so now I got to set up this horrendous equation. Oops. Okay. Oh, I'm sorry. That's 250. Just 1 second. Okay, so now we got to set this equal to 3 lambda over 2. And we know lambda already. So all we got to do is solve for x. Good luck. This is a horrendous calculation. It's a lot of algebra. I'm not going to go through and solve this, but you can do this really on your calculator. I mean, you can actually do it iteratively just to find the value of x such that the left side of the equation equals the right-hand side of the equation. Okay. I'm just showing you what happens when you don't make this approximation. The problem gets much more algebraically messy. We could not use this method, these equations here, because these two distances are comparable. Most of the problems you're going to be doing in the homework, they are way different, and so we can use that equation. The math is way easier. Okay, one thing I noticed wrong. Sorry, I should switch these two, otherwise this becomes negative. I made the bigger one when it's a smaller value become a positive number. Otherwise, I'd have to set this to a negative number in order to solve it. Okay. So let me recap. If I want to find what the next minimum is, that's when the path difference is 3 lambda over 2. I'm assuming the car's driving north. I guess I can have the car driving south, but let's assume the car's driving north. I could set the path difference equal to 3 lambda over 2 because in the previous problem it was equal to lambda over to lambda. And then I just find if this is x, then I just take this distance minus that distance and set it equal to 3 lambda over 2. solve for x, and then compare it to the 400 meters, and it'll tell me how far I have to drive. And that's it. But the algebra is tedious. Let me do another example. This time, something that's a little bit more, a little bit easier to do. We have red light from a helium neon laser. It's incident on two narrow slits separated by 0.2 millimeters. So D is 0.2. Fringe pattern is observed on a white sheet of paper held a meter away. So now the ratio of D over L is really small. We want to find the location of the first dark minima, and we want to find the location of the sixth bright fringe. All right, so let's set this up. That problem is, or this one is much easier than the previous one that I did. I will be using these equations. So let me draw a picture. I should make it even smaller. This distance is 1 meter. This separation, not to scale, 0.2 millimeters, which is 2 times 10 to the minus 4 meters. Lambda, 632.8 nanometers, which is 632.8 times 10 to the minus 9 meters, because a nanometer is 10 to the minus 9 meters. Let's find the location of the first minimum. So find the location of the first minimum. Okay, so I'm going to use this one. The first minimum will occur when m equals 0. So I'm going to have d sine theta equals lambda over 2. Sine of theta is lambda over 2d. Lambda is 632.8 times 10 to the minus 9 divided by 2 times d, which is 2 times 10 to the minus 4 meters. If you do this, if you actually calculate this, 632.8 times 10 to the minus 9 divided by 2 times 10 to the minus 4, this comes out to 0.0016. Theta, if I take the inverse sine, is 0.0906 degrees. This is a really small angle. So I can use the fact that sine of theta is approximately equal to tangent of theta. The location on the screen here, where I get a minimum, is going to be y equals tangent of theta. Well, it's equal to sine theta here. So we can say that since theta small, y equals L tangent of theta is approximately equal to L sine of theta, which is approximately equal to L times m plus 1/2 lambda over d. And I'm going to put m equals 1. And if I do this calculation, I'll get .00158 meters. And in millimeters, .58 millimeters. In fact, you will observe this above the central axis and below the central axis. So really, the location of the minimum can occur above and below the central axis. So I can define y to be positive above, making m positive, and then negative below. That would make m negative. So m can either be positive or negative here. Okay, it just depends on how I define my angle. If I define my angle to be positive, I make m positive. If I define my angle to be negative, I can make my m negative. Okay, except in this case, m is 0, so that one's a weird one. So 1.58 millimeters above and below the axis, I have my first minimum. Here I have a maximum, and then here I have minimum. Okay? If I were to plot the intensity, what would that look like? I'll show you a plot of the intensity in a second. Now, the next question is, where is the sixth bright fringe? Actually, before I do that, let me just do this with the trig. I want to compare to this. Okay? I'm going to use this angle, y equals 1 meter times tangent to 0.0906 degrees. Just so you get an idea of this. And you get the same answer. Okay. Now what about the sixth bright fringe? Of course, that can occur above and below the axis. In fact, I can make the sixth bright fringe is m equals 5, because don't forget, m equals 0 is also fringe. So first fringe, second fringe, third fringe, this is the 0th order fringe. So let's look at the m equals 5 fringe. And that can be above and below the axis. You're going to do a lab where you're going to measure the location of these maxima and minima. Okay, so let's let m equals 5. And so sine of theta and d is 2 times 10 to the minus 4. So remember, this is for constructive, m equals 5. Sorry, it's hard to see that. So what does this come out to be? 0.01582. And then that means theta is equal to 0.906 degrees. The angle is still less than 1 degree. Since the angle is still less than 1 degree, I can still use the approximation that sine of theta equals theta. Okay? So, and then remember, sine of theta is just m lambda over d. But m is 5. If you plug in the values, you will get 15.8 millimeters. Or 0.0158 meters. Okay? Again, if you want to use this angle, you can, but you can tell it's obvious that, I mean, sine of theta is this value. Okay? Sine of theta is this value. That matches this. Remember, L is 1. Okay? So, if you have any questions on these problems, please bring them on Monday. And so what I'm going to do on Monday is do 2 more interesting systems, or one of them I have to actually demonstrate in order for you to understand it. And I don't want to do it now because that one's going to be kind of hard to understand without the demo. So I'll stop here.